Let's start with electric flux. Okay, so what is flux? Well, let's start with our understanding of symmetry. So we have some different shapes that we've defined in this class, right? And remember, symmetry, that's got the symmetry of the charge distribution usually matches the electric field symmetry in some ways. So what are the things we know the electric field for? There's three objects we've derived. Yeah, we start with a point charge, right? That's the most basic one. So that's Coulomb's law. Okay? So we have the electric field of a point. Right? So that's K, Q1, well, just Q, over R squared in the R direction. All right? Then we have an infinite line charge. That's 2K lambda over R, also pointing out, but sort of in a different configuration. And then we also, just last time, we figured out what an infinite plane looks like, also known as the infinite sheet of charge, if you're Russian.
Do you have a Russian teacher at some point teaching this to you?
Yes.
Okay, so
I learned it from a guy named Yuri Kulomensky, and he had a really great accent. It was just wonderful. Until you were like, what is he saying? We don't have a lot of native speakers in physics. It's like, it's like 50-50. So you got a little like Chinese, little Russian, little.
You get really good at understanding accents.
Little Italian, yeah. Actually, one of my favorite teachers is Italian, and he was a well-dressed guy, and he was always making us feel bad for not being as well-dressed as him. Which, Anyway, he's like teaching. He's a terrifying man, right? Like he's funny, but he's always just like telling us we're idiots.
Yeah.
Which, compared to him, we work. So he's up writing on the board. He came in all black. Like he's wearing a three-piece suit. It's completely black. He's got a black shirt, black tie. And he just comes in and he starts teaching and he's writing on the board. And then he just he's writing, he's doing an integral. He turns around and he goes, I am the angel of death. And he just keeps writing on the board. So, anyway, these are my teaching inspirations. So, plane. What's special about a plane? What's the formula? There's one really important thing to remember about the infinite plane. How does it depend on R? It doesn't, because it's a constant. There we go. So eta over 2 epsilon naught in the R directions. Okay? And all these R directions are slightly different R directions, right? Because remember, the infinite plane has this sort of symmetry. So above the plane, the electric field lines point up. Below the plane, they point down. Okay, but they're always perpendicular to the plane. All right. What about the infinite line? What does that look like? What kind of symmetry would you say that has? Yeah, it's like a cylinder, right? And so the lines pierce the cylinder. They're perpendicular to the cylinder. Okay? And then a sphere is a lot like a point charge. You have electric field lines pointing out in all directions. Now these are all pointing away from the charge because these charges are positive. Okay? If they were negative, what do? Yeah, you change the direction of these arrows. Okay? So this is for things that are not conductors, which are insulators. Okay? You can also do this for conductors, and usually in order to have these sorts of charge distributions, we do these for things that are like capacitors. So this would be our parallel plate capacitor, okay, which is just a positively charged plate and a negatively charged plate. But these are conductors, all right, so things can move around a little bit differently. But this has very similar symmetry to here. What is the electric field like in here? Which way would it point? It's constant, but does it point up, down, to the side?
Point down, isn't it?
Points down. It points from positive to negative. So you have a bunch of arrows that would point down. Okay? You could also have this. Maybe you've seen one of these someplace before. like a long metal tube with a metal wire running through the middle. Probably have one in your house if you have cable or broadband internet. Yeah, this looks like a coaxial cable, okay, which is a conductive thing. So the electric field for this is going to look a lot like that one, okay? And then for a sphere, you're just going to have arrows that either point in or out depending on whether you have positive or negative on the inside or outside, okay? So these, just to give you some words that we use, this is the infinite parallel plate capacitor, okay? These are coaxial cylinders. What do we mean by coaxial? Like, break that word down.
Two axes.
It's a shared axis, right? So the central axis is the center of this, and it's the center of this, so coaxial, all right? Concentric spheres, that just means shells that are all centered at the same point, so shared center, okay? Okay, so we get electric field lines when we have charges. So if we know what the electric field lines are, we can guess what the charge distribution looks like. Okay, these are all very symmetric, but if they aren't, here's a problem I want you guys to talk to each other about. It'll take about 5 minutes, and decide what kind of charge is inside these. Like, these are just like little arbitrary bubbles, so you can't see what's inside them. Okay, they're not actually charged or anything, but there's charges inside, or not. So I want you guys to try to figure out, just based on the electric field lines, what kind of charges are inside that little bubble. This guy, what kind of charge is in here? Negative charge. How do you know it's a negative charge? Because the arrows point in, right? Arrows point away from positive charges and towards negative charges, okay? So this is a negative charge. What about this one? A positive charge. Would you say that this charge is bigger or smaller than this charge? Bigger. Bigger. Why do you think it's bigger?
More arrows.
More lines, right? So more electric field lines, more dense electric field lines means a stronger electric field, which means you probably have more charge, okay? And they're going out, so that must be a positive charge. What about this one?
Negative on the left side and positive on the right. No charge first.
Actually, the electric field lines don't change really at all. They just go through it. So there'd probably be some positive charges out here, and maybe some positive charges over here, and some negative charges over here. But there's nothing in here.
Okay.
Okay? What about this? So that would be a dipole. Okay? So remember, things go towards negative charges, so there's probably some negative charges over here, and some positive charges over here, and that means this is still going from positive to negative, okay? And this should look a lot like, have you ever taken metal shavings and sprinkled them around a bar magnet, right? If you look at the magnetic, okay.
All the time.
Has anyone ever done that? Okay, one person. Never mind, this is no longer a cultural touchstone. So, we could do it later if you want, but I thought poor people were just given metal shavings as kids.
First thing I did.
If you played with magnets, right, you know that the magnetic field kind of loops around from north to south. Yes? Maybe? No? Well, you will know because we're going to do that later. Okay, so let's talk about flux. So before we talk about flux, we're going to define something very abstract called a Gaussian surface. Okay? Now, a Gaussian surface is an imaginary closed surface. So imagine a closed surface, all right? And so it's basically any shape. It could be a sphere, it could be a cube, it could be a cylinder, it could be a pyramid, it could be some bulbous cloud, okay, as long as it's closed. And what do we mean by closed? Like a complete thing. There's no holes in it, okay? So the whole shape comes all the way back around, all right? So a Gaussian surface is any imaginary closed surface. And we're going to need this to we're going to do some like kind of hand-wavy vector calculus. And what I mean by, you know the term hand-wavy? So in physics, there's rigorous proof where you go through all the math, and then there's the hand-wavy explanation where you're like, well, it's kind of like this thing and you wave your hands around to distract people from the fact that you're not really being very rigorous, okay? So we're going to do the hand-wavy explanation because a lot of you haven't taken vector calculus, and going through divergence theorem is also kind of dull. And it doesn't necessarily help you to understand what we're going to need to do to solve the problems. But if you really want to get into the nitty-gritty of how Gauss's law works, you're going to have to learn divergence theorem, but you don't have to do it yet, okay? So a Gaussian surface is any imaginary closed surface, and it has to be a closed surface. This is really important for the math to work, okay? Because divergence theorem, which we don't know, but it's this closed surface, and you have to integrate over this closed surface at some point. But the trick to using it is to pick such a good surface that you don't have to do the integral. So you want to set up an integral that's so amazing that it doesn't have to be integrated, okay? And that is the whole thing we're doing with Gauss's law. And this is why we introduced these charge distribution integrals we did in the last chapter, is so you can fully appreciate how much easier it is to do Gauss's law. Yes? No? All right. So so let's say this is an imaginary closed surface. This is a good Gaussian surface. What sort of structure, what sort of charge distribution would you imagine is inside this surface? Positive. What shape? A cylinder or just a line, right? A line charge going up through here. And so you have electric field lines pointing out in all directions. So you pick this shape, right? So that the electric field lines pierce through it. That's how you're going to calculate the electric field, okay? And so here you can see, just looking at it from different sides, it's going to be perpendicular to this surface at all these points. It's either perpendicular or parallel, right? So it's perpendicular to this surface, it's parallel to these. And this will be really important later because Gauss's law includes a dot product, okay? So dot products are annoying if you have to do angles that aren't 90 or 0 or 180. All right, so we're gonna try to pick angles where we don't have to do the dot product. Remember, the electric flux, once we define our surface, is the amount of electric field passing through that surface. So we want to set up our surface so that the electric field pierces it. Okay? Now, you don't have to pick a good Gaussian surface to actually calculate the flux. It just makes the problem a lot easier. And you'll see what I mean in a little bit. Okay? So we're basically constructing a method for determining the electric field that's much easier than doing these really rigorous integrals that we use to get this and this. All right? So we want to make a closed surface. We want to describe the electric field coming out of the surface. So those random shapes like before, those were Gaussian surfaces. Okay? We looked at those Gaussian surfaces and we could establish what kind of charges were inside them just by looking at the field lines. Okay? Conversely, if you know the charges that are inside them, you can sort of guess what the field looks like. And this is what we're going to do mathematically with Gauss's law. So it looks like an integral. It's not. Okay? It's just knowing geometry of shapes like those. All right. So useful Gaussian surfaces have a few rules. The electric field is the same at each point on the surface. So that means if you pick a Gaussian surface like this, the electric field everywhere on the outside of the cylinder should be like 6 newtons per coulomb, okay? It shouldn't be 6 one place and 5 some other place. It shouldn't be 6 up here and 2 down there, okay? It has to be this exactly constant everywhere on the surface, all right? The electric field also has to be either perpendicular at each point on the surface or parallel at each point on the surface, and that's because we're going to lead into this dot product, okay? So once again, symmetry is your friend, all right? So here is a question. So there's going to be a net negative charge, and how do we know that?
Just more arrows going in and out.
Yeah, there's more arrows pointing in than there are pointing out, okay? So that means there's probably more negative charges than there are positive charges. Okay, so let's talk about calculating flux, all right? So, anybody, I know did we talk about flux capacitors?
Yeah.
Yeah. Oh, I got an email. Kragen has a flux capacitor listed on their website. It's actually not the first time I've seen that, but it is still pretty fun.